Thanks. I will begin. Dear Father, we thank you for this day. I thank you for the students, and just ask you to bless this class today, Lord. In your name I pray. Amen. All right, let me start with the Theorem 3 one more time. What's Theorem 3 say? It says let F be field, P of x in the polynomials over the field irreducible. All right. Then there exists a field K extending F such that P of x has root in K. So the construction was what? Here's the construction. We let K equal f of x, fx mod the ideal generated by P of x, all right? And I remember from last time, I'm going to call that I. Then, if we look at pi, a mapping from, let's see here, pi of, how's it go? Pi of, oh, curses. I think I'm doing. So I think pi of f of x is equal to f of x plus I. It's the coset map. That would make pi go from where? Right? That is a homomorphism, right? Like pi of f of x times g of x would be what? By definition of coset multiplication. And likewise, pi preserves addition. Great. So the claim is that, let's see here. So I want to argue that the polynomial P of x has a 0 in K. How do we do that? What's that mean? It can't be a literal, it can't literally be a 0, right? Because what? Oh, by the way, I'm I'm forgetting to say something here before I get over to that. There's something I'm supposed to say here, which is this is what? This is a homomorphism into where? A homomorphism of rings, right? Into a what? a field, right? Because why do we know that K is a field? Yeah, P of X is irreducible, which means that I is a maximal ideal, so the quotient by a maximal ideal is a field. So what does that say about pi of, what's that say about pi of F? In here I mean really pi of F times 1. This is kind of silly, but I'm talking about like constant polynomials. Pi of constant polynomials. Well, I guess what I'm trying to ask is this homomorphism, is it the zero homomorphism or is it a non-zero homomorphism? And what did we say about homomorphism? Proposition 2 says phi going from F to F prime, a homomorphism of fields, then either phi is either identically zero or it's injective, right? So the image, now, well, I guess, oh, curses, that's a, oh, I need a homomorphism of fields, right? So how could I get a homomorphism of fields here? The restriction, right? If I look at the restriction, pi restricted to just constant polynomials. Let's say, let's call that, well, let's call it F, if that's okay, right? Restricted just the constant polynomials, then you've got a mapping from F over into K, right? That is a ring homomorphism of fields, right? If we restrict the pi map just to the constant polynomials, then we've got a mapping from field to a field, which either has to be injective, right? Or what? Or zero. It's not the zero map, though. So what's this say? Right. So therefore, pi restricted to F of F is, you know, that is isomorphic to F, which is a subset of K. Anyway, the point is that there is a natural copy of the field inside K, right? Like we talked about last time. It's, yeah.
When you say constant polynomials, do you mean polynomials with only a constant term, no x?
Right.
Okay.
Yeah. Okay, so great. Now, why is it that we have a zero, right? So he just calls this thing phi, and he says, okay, so, you know, he says, well, phi of F is isomorphic to F, which can be viewed as a subset of K, right? There's a natural copy of F sitting inside the extension field K. Okay, so then, why does P of X have a zero in K? What's that mean? He writes this. He says P of X bar. What's his X bar? See, P of X bar is actually P of pi of X. In other words, it's P of X plus I, right? In the other notation. Anyway, as we went through last time, you can argue that that's equal to P of X plus I by just the usual rules of, you know, coset multiplication and addition, right? But what's special to this context is that P of X plus I is actually equal to I again, right? I mean, this is equal to I again, or more to the point, you could say it's equal to 0 bar. So in this context, in the extended viewpoint, this polynomial has a 0 in this extension field, right? In the sense that if you plug in the coset, it works out to the 0 coset. Any questions about this? No? Okay. Now, notation. We would rather use well, okay, so notation, we'll use 1 bar equals to 1, okay? X bar equals to theta. X bar squared equals to theta squared, et cetera, et cetera. X bar to the j is theta to the j, where, so like theta to the j is of course equal to x to the j plus I for j equals to 1, 2, n, well, n minus 1, but I mean, you could go past that. It wouldn't be wrong. It's just, what's the point here? How do you calculate in k is the question, right? And so here's what he says. He says, if we take a of x plus I and b of x plus I, right, and we want to multiply these, all right, then how do you do it? You look at a of x times b of x, right? And that's going to be equal to what? It's going to be equal to something like q of x times p of x plus r of x, right? And so, long story short, we have the following. We have like a of, well, really, a of theta times b of theta equals to r of theta. See, because the whatever piece is a multiple of, whatever piece is a multiple of, come on, top hat. Stop being stupid. Oh, you can't stop being stupid. It's who you are. I shouldn't judge it. Come on, give us a meaningless number to poke into a meaningless website. All right. Here we go. 5, 6, 8, 7. One. 2, 3, 4. How many should I get to? Probably 6. I got 4. Once I get to 5, I'm resetting it.
Resetting?
Okay, I'll let it get to 6. All right, close 10. That's great. Here you go. 3, 9, 4, 7. One more time? Yeah, okay.
Myself are all in now.
Yeah, I got 6. There we go.
One more.
3, 4, 7, 8.
You were just wreaking havoc on the system.
I wanted to try to do 2 at one time, but I haven't quite figured out how to make that gel.
I told some people in linear and Calc 2 about Top Hat weekend. Oh, I saw a lot of people about it. They're excited.
You know, once you start doing this, it's really hard to stop.
Oh, we're doing it again?
6, 6, 4, 1.
Oh, yeah, wait.
Oh, about to lose your chance.
4, 1.
About to lose your chance.
Okay, I'm present.
Our attendance grades are going to be stellar.
All right, one more. 3, 2.
This makes up for us.
Yeah, this makes up for all those days I forgot. There we go. Now Gentry had a fantastic idea. He said at the start you should just like do them all, but just have dates and like just say date you're going to attend and just like get it all done in one day. Get all the attendance done in one day. I like Gentry. That's just brilliant. I said it's brilliant.
Imagine all 75 days in one class.
Yeah.
I mean, we just did 5 in a matter of like. If we did one more, that'd be 2 weeks done.
So do you guys understand what I'm saying? So the idea here is to calculate in this extension field. You could to actually do it, right? You do the Euclidean algorithm, and find the remainder term, and that's really what the representative is of the product, right? The product is the representative of the remainder. The basic calculational tool here, I mean, the calculational essence of this, the calculational core of all of this is simply that this construction is just engineered so that p of theta is 0. All right? P of theta is 0. That is the quintessential fact about this construction. And of course, that k is equal to the span over the field. Sometimes I double bar my f's. My apologies. I can't remember which class I'm in. 1 theta squared, theta to the n minus 1, right? And we argued that that's a linearly independent set. All right, last time. So, if there's some really kind of like low-hanging fruit here. If p of theta is equal to a sub 0 plus a1 theta, really I'm saying, I mean, you could replace the theta with x here just the same, right? So if you got all this, then what's the inverse of theta? Multiplicative inverse, of course. You're like, how do you know that the multiplicative inverse of theta exists? Well, it would sure be very embarrassing if the multiplicative inverse of theta didn't exist. We just said this was a field. Theta is certainly non-zero, right? So if this is all right, short of something really obnoxious, like how could it be that theta inverse wouldn't exist? There's really only one case, is if your p of x is equal to what? Not, well, 0, kind of. But how about p of x is just equal to x? Right? If you look at f of x mod the ideal generated by x, well, you just get back f again, right? So in that case, the idea is essentially that you're just setting x equal to 0. So if you look at polynomials in x, they just down to their constant term. And that's that. Ignoring that, this is interesting. And so what could you do? Is a0 non-zero? P is irreducible, right? That means it cannot be reduced. If a0 is 0, that means we can factor out x, and x is 0. In other words, it has a reduction. So that can't be the case. We know that a sub 0 is non-zero by assumption of irreducibility. And so that means I can do what? I can take all of this and I could put a1 plus a2 theta plus plus an minus 1 theta to the n minus 2, factor out a theta, and set it equal to minus a sub 0, right? And then all you got to do is divide by the multiplicative inverse of a0. And so that gives us that theta inverse is actually equal to minus a0 to the minus 1 power, and then the thing in parentheses, a1 plus a2 theta plus plus an minus 1 theta to the n minus 2. Now, calculating the multiplicative inverse of other elements in this extension field is more involved, right? But this is something that's relatively easy to do, to actually find the multiplicative inverse of the theta in the extension. So, another way to talk about what we're doing right now is to say that we're adjoining k. I mean, what is k? K is f adjoin theta. In other words, we could say k is equal to f theta like that. Right? So a nice example that is, relatively easy to calculate in, of course, and is important, and we've talked about it before, but I'll talk about it again because it's important, is the, yeah.
So last semester,
Parentheses, yeah, parentheses still have the same meaning here. Parentheses is a field. Bracket just means the ring. It's a ring. And I have, there is example 7 in this section. Hopefully I'll get to it. Let me get to it. So we can look at the reals adjoin theta with theta squared plus 1 equals to 0 as what? As like r of x mod the ideal x squared plus 1. Right? This is equal to a plus b theta such that a and b are real numbers and theta squared is, well, minus 1. And by the way, is here p of x is x squared plus 1, right? That's an element of real polynomials, and it's irreducible because it has no real 0, right? All that stuff we talked about irreducibility last semester, it still matters. Eisenstein, that other weirder stuff, it all matters. Okay, so let's try to, my boxed equation over there, let's take it for a spin. So allegedly here, we have theta, okay, so I got like theta squared plus 1 equals to 0, right? Or I guess if I wrote it in the same staff, I'd have like theta 1 plus theta squared equals to 0. So 1 is equal to theta times like minus theta, right? So you can see from this, theta inverse is minus theta. Of course, you guys know this already, right? Like 1 over I is equal to minus I, so that's not surprising. There's an obvious isomorphism, psi, from the complex numbers to the reals with theta adjoined, right? And that would be what? Just that, right? This is, in fact, an isomorphism. So, up to isomorphism, complex numbers are nothing more than real polynomials modulo the ideal generated by x squared plus 1. We talked about this last semester, but I think it's good to come back to it again.
I have a quick question.
Yep.
So you wrote down the word proof at the beginning of this whole thing.
Yeah.
So is that the end of the proof?
Oh,
Like when you found
I think that the truth of the matter is the proof was distributed amongst this class and last class where I proved the independence of the, I'm not sure, you better look at Dumb and Foot. My proof in here is, I think my proof has become fractured.
Okay, gotcha.
My apologies.
I was just wondering if there was any
Yeah, proof is probably too strong a word. I should have used something other than proof there. Yes, exploration would be a good term. Maybe abuse. I don't know. Anyway, hey, let's look at another example. And this is, well, you could look at Q. He says, look at Q of x mod this, right? And what you would get is up to isomorphism Q adjoin I, right? If you want to go back to the theta notation, you could say it's Q adjoin theta, right? I mean, this is literally in his setup Q adjoin theta, which is A plus B theta such that, A and B are rational, and theta squared is minus 1. So this is, related but different. I mean, I would say Q adjoin I is, of course, a subfield of the complex numbers, right? Q theta is, of course, isomorphic to that subfield of the complex numbers. And we kind of like to stop worrying about isomorphic versus subfield. We'd like to say up to isomorphism when we talk about these things. So I'd like to just say Q of theta is a subfield of the complex numbers with the understanding technically that means it's isomorphic to a subfield of the complex numbers. Similarly but different, if we look at Q of x mod the ideal generated by x squared minus 2, of course, x squared minus 2 is irreducible, right, over the rationals by Eisenstein, p equals to 2, right? So this looks like a plus b theta, such that what? A and b are rational, and what's the deal with theta? Theta squared is minus 2. So in this fun new world of Q adjoin root 2, if if you're asked something like, I don't know, here's 3 plus 2 theta, what's the inverse of that? How would you calculate that? How would you find the multiplicative inverse of 3 plus 2 theta in, Q adjoin theta here? You're like, yep.
Should theta squared be positive 2?
Oh, yeah. Thank you. You're like, well, I'd stop being weird and right, so that's the thing is sorry, I don't have words for what I'm about to say. Let me see here. He says if we denote theta by the square root of 2, see if I did that. And then I go, well, that's 1 over 3 plus 2 root 2, then you know what to do, right? You've been taught a long time ago, you multiply by 3 minus 2 root 2 over 3 minus 2 root 2, right? And you know that's going to rationalize the denominator, right? And what does that give us? It gives us 3 minus 2 root 2 over 9 plus 2 times, 9 minus 2 times the square root of 2 squared, right? Otherwise known as what? 3/5 minus 2/5 square root of 2.
Isn't the 2 also squared?
Oh, curses. 2 is also squared. You got a point there. So that's, what?
That's just the conjugate.
So that works out to 1, huh? Well, those are kind of boring rational numbers, but I'll take them. So apparently 3 minus 2 root 2, huh? That's funny.
Wait, earlier you said that the inverse is minus theta. Is that why?
The inverse was, no, there's a context to that. The inverse being minus theta is over here. That's a different world. Which is, by the way, hilarious. But anyway, yes?
Why is it hilarious?
It's from another time. Let's see here. You guys don't know a different world? The spin-off of The Cosby Show. Let's see here. Like I said, it's from another time. Let's see here. Okay, so the thing this is very actually kind of interesting. So it's almost like this is a very funny calculation.
I feel like it's just a good choice of numbers.
Yeah, I got lucky, is all it is, or unlucky, depending on your viewpoint. But look, we said that theta was equal to the square root of 2 in that calculation, but if you really look at what we did, all we did was use that the theta squared was equal to 2 in the calculus of it, you know? If we had used minus 2 instead of root 2, it wouldn't have been any different in some sense. I mean, it was like there would have been... I would just point out that, you know, there's this here, this q of x mod x squared minus 2. I think we could either look at it as being q adjoining the square root of 2, right? Or we could look at it as q adjoining minus the square root of 2. It wouldn't have... And I think these are the same... I mean, those are the same field, right? Those are the same field extension of the rationals. That's all. I'm not saying anything terribly deep here. Next up, this one's a little bit fussier. A little bit fussier. Here we have, and this is example 4. Let's see here. So q of x mod x cubed minus 2. All right. So this is, you know, isomorphic to a plus b theta plus b theta squared, c, good grief, c theta squared, such that a, b, c are rational. And what's the deal with theta? Theta cubed is 2. He says this is a degree 3 extension over the rationals, right? And he gives us the calculation of like what's the inverse of 1 plus theta in this field. Maybe that's interesting to work out. Here's a sample calculation. One plus theta inverse is what? All right. I mean, we're looking for 1 plus theta times, let's say, I don't know, lack of imagination, f of theta equals to 1, right? But really what that amounts to is I mean, I guess we could work it out like that. I mean, I don't know. So a plus b theta plus c theta squared. And so I guess you can always look at it as 3 rational equations, right, and 3 unknowns. This would give me a plus b theta squared plus c theta. Oh, good grief. A plus b theta plus c theta squared plus a theta plus b theta squared plus what? Theta squared was 2. Theta cubed was 2, right? So plus 2 plus 2c equal to 1. So in other words, a plus 2c equals to 1. B plus what? B plus a equal to 0. And so this is from the constant coefficient. This is from the theta coefficient. I'm using linear independence of 1 theta and theta squared. Theta squared, I got what? I got a c plus b is equal to 0. So from these two, what can you see about the relation? What's this say? This says a is equal to c, right? If b plus a is 0 and c plus b is 0, it must mean that a is equal to c, right? And therefore, 3a is equal to 1. A is 1/3. C is 1/3. What's b equal to? Apparently, minus 1/3. And so there you have it. 1 plus theta inverse is equal to 1 minus theta plus theta squared, all divided by 3. Now, I think the way he does it is smarter. He uses Euclidean algorithm to find a of x and b of x such that you get 1. And he derives the same thing, but he uses the polynomial division. All right. Do you guys remember how that goes? I'm a little rusty personally. Yeah. I mean, he says that we can find a of x times 1 plus x plus b of x times x cubed minus 2 such that we get 1. Why would you find, how would you find a of x and b of x like that? What would you do? He says, by the way, this has to be the case because since p of x, x cubed minus 2 is irreducible, that means it's relatively prime to any smaller degree polynomial. To say otherwise would to say that would mean that it has a common factor, which I think would imply that the p of x has a 0. And anyway, so if it's relatively prime, that means there's like, by the sort of Bezout theorem, but for polynomials, we can find an a of x and b of x like that. How do we actually do that, though? What was the algorithm? Do you remember? I think it basically comes from looking at, think about x cubed minus 2 divided by 1 plus x, right? And if you think about that, that's going to give you what? A quotient, right? And a remainder. What's the remainder, though? Good grief. So this is, that's, I can't say words today. X cubed minus 2 is q of x times x plus 1, right? Dividing by x plus 1, and then plus the remainder. But the remainder, since it's relatively prime, is nothing more than 1. And so if you rearrange that, it gives you the thing above, right? Identifying, I guess that means the, anyway, let me stop talking about this. I have nothing to add here at the moment. I mean, personally, I don't know. I'm, my unnatural love of linear algebra. So like, I prefer this method, frankly, although if you're fast at polynomial long division, that could be labor saving if you understand how to do it that way. Also, for more complicated example, don't forget about my brother's website, which finds the sort of the Bezout coefficients for to find the GCD of two polynomials. Remember that applet I shared with you guys? That can at times be really helpful for certain homework problems. Okay, anyway, I think if I actually took the time to divide x cubed minus 2 by x plus 1 here, we'd derive this pretty fast, because it would just be what's in the numerator. So I'm selling that method short by not doing it, yeah? Next up here, and this example I think you'll find, well, there's a little bit more to say about my current example. Oh, but he doesn't say it yet. All right, fine. This example is important. We'll come back to this one, all right? The reason this is important in part is well, I mean, obviously you can look at this as q adjoin the cube root of 2, right? But what about, I mean, that's a third order polynomial. What about the other two roots? whatever. What about the other two roots? Well, we'll come back to talking about that. But the interesting thing is the field, if you look at the extension field as being the base field that join roots, one of the theorems we're going to find is that any of these are isomorphic. So like the field formed by adjoining either of the other two complex roots of this third order polynomial will again be the same field up to choice of notation. But those would no longer be real fields. They would be, I mean, we can view this as a subset of the reals, right? Algebraically, if you look at the set, say A plus, let's say here, B, I'll call it zeta, plus C zeta squared, such that zeta is the cube root of 2 times, let's say, a third root of unity, e to the 2 pi I over 3. And here, of course, ABC rational. What I'm trying to say to you guys is that this field, Q adjoin zeta, in that sense, that is isomorphic to Q adjoin root 3. And it's also isomorphic to the extension field I'm talking about in this example 4. Okay? So I guess what I'm trying to say is that identifying theta as the cube root of 2 is ad hoc. There are 3 roots to x cubed minus 2. None of them are rational, right? 2 of them happen to be complex. 1 of them happens to be real. Which one do you identify as being the quote-unquote theta? I mean, that's just a choice, a notational convenience. And up to isomorphism, you know, Q adjoin zeta is isomorphic to Q adjoin the cube root of 2, right? And by the way, it's also isomorphic to what's the other choice? Yeah, exactly. A cube root of 2, e to the 4 pi I over 3. Those are your 3 distinct roots of x cubed minus 2 in the complexes. And we could look at the extension field as taking the rationals and adjoining any one of those, really. Okay. Now, example 7, we'll get back to your question about the brackets because it's kind of weird. Yeah. Go for it. It's fine.
You had the, like, right next to example 4, you said that q over x, q of x mod x cubed minus 2, that ideal is isomorphic to that set.
Right.
But we are allowed to say that that set is equal to.
Yeah, I think we could say equals given our discussion today. Sure. Yeah.
Okay. But then these sets are not equal down here. They are isomorphic.
Those are isomorphic, yeah. Because they can't be the same thing, right? Because this is subset of C, right? This guy you could view as a subset of the reals, and this, on the other hand, is a subset of the complexes. So they're not equal, but they are isomorphic, yeah.
How come, so now that that's equal up top, it's also equal to the cube root of 2?
Which one, where, what?
So now that you made the top row equal, so that all of that's equal now?
These?
No, the top row.
Very top.
You just changed it from isomorphic to,
Oh, yeah, I mean here, yeah, I mean, fine, yeah.
Oh, okay, wait, so now, yeah, that is, okay, so then q of zeta is isomorphic to a plus b zeta plus c zeta squared? Wasn't that, is that zeta? Oh, it is.
Zeta, yeah, yeah.
Okay, right, so would that be isomorphic, or would that be equal?
That's equal.
Okay.
Because I'm just taking the rationals and adjoining zeta.
So then,
Oh, but a plus b theta plus c theta squared, that's isomorphic because it's not necessarily equal to it. Because it could be, because theta.
What is theta? I mean, theta, you
Right,
could
theta-
choose
theta could be any of those three things, any of those three options.
in principle, but in practice, we're really wanting to say that the theta is the stupid coset. I mean, it's the set of cosets. It's not stupid. I'm stupid, but let's see here, usually. But if this is a set of cosets, then this is not equal. It's just isomorphic, right? But I'm sorry, I'm majoring in the thing that we soon want to identify, so we are spending far too much energy on something that we will soon just think of as the same thing. So,
Okay. I just wanted to check.
well, all right. So, example 7 was the one I mentioned, and this one's a little bit different. So f is k of t. So this is actually equal to like p of t over q of t, such that p of t, q of t are in k square bracket t, q of t not equal to 0. This is the field of rational functions in T over K. Field of rational functions in T over K. And what he does here, and this is also interesting, he says let P of x equal to x squared minus t. This is in the field above. And this might catch your eye. He says that P of x is irreducible. How does he argue it's irreducible? By Eisenstein. You're like, wait a minute, what do you mean by Eisenstein? I thought Eisenstein was about polynomials over with rational coefficients, right? Well, the Eisenstein theorem, the Eisenstein criteria extends to more general fields, all right? And so that same, what was the Eisenstein criteria? We had it was irreducible if what? If P divides, how did it go? The prime, we had to find a prime that divides each what? Each coefficient? Besides the, it's for a monic polynomial, right? So you take a monic polynomial, and if the prime divides every non-leading coefficient, and then what else did we need?
Oh, but p squared doesn't divide the constant.
P squared doesn't divide the constant term, right? Then Eisenstein says it's irreducible. So what's the prime here? What prime is he using? You say, Eisenstein using prime t. So t is prime in here. So you had to think about what that means, right? But if you do accept that, it's clear that t certainly divides the non-leading term, and t squared does not divide t. So this is irreducible, which then means that f, right, f of x mod p of x is what? That's an extension. It's an extension of f by essentially what? Square root of t. So what does it look like? Things in here would look like a of t plus b of t times theta, such that what? Theta squared equals to t. And here, b of t and a of t are actually what? They're actually rational functions in time, in t. So I think this example is considerably more adventurous than the other ones we've looked at today, but I think it's an interesting example. So I think, roughly speaking, it's kind of like what? You go from rational functions, and it's like an even bigger set of functions that forms a field. What kind of functions are these? I mean, algebraic functions, right? But just involving like a square root in that sense? I don't know. An example of a function field.
Why are you allowed to say that t is a prime? Why are you allowed to just kind of assign, like, say we're going to use...
Why is t a prime? What do you guys think? What was our definition of prime?
Oh, shoot.
That's right.
Is that the one with, like, co-relatives or whatever those things are called? Do y'all remember this?
I
So that's the question, is how did we define prime? You go back, you look at that, you'll be able to prove that t is prime. So, yeah. We should all do that, right? We should all do that. Euclid's lemma is useful. Like if how's it go? I'm not going to try to do it right now, but I'll shut up. Thanks, guys.